Hello dear students, welcome again to the tetrahedron chemistry classes. So in today's lecture, I am going to discuss another very important organic chemistry reaction mechanism problem which will enhance your ability to solve the multi-step organic reactions, and the name of the topic is again the same, Ace Your Reaction Mechanism Skills, and this question I have taken from the GATE 2020 examination. And this question is very important in order to understand the various types of the functions of the various types of the reagents and the stereochemistry and lots of things, right? So what is the question? Let us see first what is the question. Major products P and Q in the given reaction sequence are. You have been given this particular starting material which is your ester, okay? And it is not this ester, though it is not conjugated with the ring, but it is, again you can see that ester is connected with the cyclopentadiene ring. And in the first step you are taking this particular reagent, and the abbreviation of the reagent is given in the question itself, 9BBN, and one equivalent you will take to start the reaction, okay? And in the second step, you will take your sodium hydroxide in presence of the hydrogen peroxide, and with the help of these two step reactions, right, you will produce one intermediate P. That P in the step 1 will react with the MsCl and in presence of your triethylamine, and in the second step you will do your you can say the alkaline hydrolysis type of thing, NaOH. And in the third step, you will do the hydrogenation in presence of this particular catalyst, and finally you will get your product Q. So you have to identify what is the P and what is the Q. Right? To understand these types of the question, it is very important to know the functions of the reagents which are given in the reaction itself. Right? So first of all, you can see here, I am starting here, see this is product P. And you see here the stereochemistry is given here. This is below the plane, and in the stereochemistry, you know, this dashed or the hashed wedge shows the group which is below the plane, right? And this solid wedge shows the group which is above the plane. So this is below the plane, this is above the plane. If I see the structure of the P only in the option A. If I go in the option B, the same thing is happening also here. Here this ester group is below the plane. And in the C and D as well, this particular ester group is basically below the plane, but this is not given in the question itself. So what is the meaning of that? The meaning of this reaction is that you have to assign or you have to assume the stereochemistry of this particular group first, and it is quite a wise decision to assume the stereochemistry of this ester group below the plane, as in all the examples or all the answers given in the options, this group is your below the plane. First of all, you remember this thing. Now, what is this BBN, right? And what is this MsCl? And what is this triphenyl rhodium 1 chloride? All these things you need to know before starting the reaction. So let us take a look, right, on the reagents first. So first of all, this is your 9BBN. 9BBN is 9-bora bicyclo 3.3.1 nonane. Okay, so this is a bicyclo compound, and this is the nomenclature of this particular compound BBN. If you don't know how to give the name to the bicyclo compounds, then you can go through the link given in the description box where I have explained the detailed nomenclature of various bicyclo compounds, right? But right now you can understand this is bicyclo compound, and the structure of this bicyclo compound is this one. This is the borane, and this borane is basically having the hydrogen attached to it, and then you see here this ring is also present here. And if you want, then you can number this particular system, then you will find 8 carbons in this particular system along with the 9th your boron. So say let us start from here, 1, 2, 3, 4, 5, 6, 7, 8 and 9. See, this numbering is not according to the IUPAC nomenclature. This is just for understanding how we can count total 9 atoms. That's why it is known in here. Okay. And generally in this particular reaction, we need this boron and this hydrogen moiety to react with particular system, right? So generally we don't need this particular bicyclo thing. So in the literature way, this bicyclo ring is generally written like that, okay? And this looks like a banana, not exactly like banana, but you can assume this is looking like a banana. However, my drawing is not very perfect. It is not looking like banana, but scientists considered this boron as the banana boron. And what does banana boron do? This BBN actually used for the hydroboration reaction, and after that hydroboration reaction, you can do the oxidation as well, right? So this 9-BBN followed by the hydrolysis will give you the hydroboration oxidation, which is generally used to convert the alkene into the alcohol. Please remember this point. You will convert the alkene into the alcohol, okay? And this BBN favors the less substituted alcohol formation. This is very, very important. So if I go back, you can see here this alkene system is here, this alkene system is here. In the first step, you are reacting this with the BBN, and then you are doing the alkaline hydrolysis. That means you are producing alcohol. So you can produce alcohol on this particular system on the right hand side, or you can produce this alcohol on the left hand side system. It will not make any difference to the final product, right? And then you can see here my second very important reagent, which is your MSCl. MSCl is methyl chloride. It is just analogous to your tosyl chloride, right? And the name of this methyl chloride is basically methyl sulfonyl chloride, and this is the structure, sulfur in between, right? The in between the four groups, and these are the two oxygens. This is methyl and this is Cl, right? Basically, the role of this methyl chloride is just like your tosyl chloride. It converts the poor leaving group into the better leaving group. This is, I have already written here, used to create this methyl chloride used to create better leaving group, right? If the functional group is present and that functional group is not a better leaving group, then you can derivatize that particular functional group with the help of this methyl chloride to convert that functional group into the better leaving group. This is the important function of methyl chloride. And in the third stage, if I go back further, you can see in the third step you are having this triphenyl phosphine rhodium chloride. And if you have learned that polymer science in pretty much detail, then you know what is this. It is Wilkinson catalyst, right? And in the organometallic lectures as well, I have explained this Wilkinson catalyst in the pretty much detail. This Wilkinson catalyst generally used in the hydrogenation reaction, okay? That means the reduction will take place. So this is where triphenyl phosphine rhodium 1 chloride, and this is known as the Williamson catalyst. And this Williamson catalyst is used for the hydrogenation reaction, and the hydrogenation reaction will occur from the less hindered side. So these things you should know before starting the reaction, right? So now I am going to discuss the stepwise reaction mechanism for this particular reaction, and then we will decide which option among A, B, C, D is correct in identifying the product. I hope this is quite clear to you. Now I am going to discuss the mechanism. So first of all, I'll write the starting material, and my starting material is this one. Okay, this is, and now I am deciding the stereochemistry of this one. This is below the plane dashed wedge, and one carbon is here. This is connected with the CO2 ET. This is the starting material. Okay, and when it is the starting material, then you can do your reaction. See guys, it is very, very important to fix the stereochemistry of this particular starting material in order to get the correct product or correct intermediate P. Okay, so what I'll do here, I'll write this BH here. Right. This is my boron connected with the hydrogen. Okay. And then I am writing that banana bond structure for this one like that, right? So what basically this BBN do, it will basically give the addition reaction, and that addition reaction would be the syn addition. Please remember, it will give you the syn addition. That means this particular hydrogen and this particular moiety will add to that double bond, and both these groups, this hydrogen as well as this boron moiety, will be present on the same plane. Please remember this point. And now if you see the stereochemistry of this one, this is below the plane. That means bottom side is sterically hindered. So the only thing which we can do, we can attach this, or we can attach this hydrogen either to this carbon or this carbon, this carbon or this carbon, or this boron either to this carbon, this carbon, or this carbon, this carbon, but from the top phase or above the plane. So I am not writing the exact mechanism of the hydroboration reaction. If you don't know what is the hydroboration reaction, again I am giving you the link in the description box. By clicking on that particular link, you can understand the hydroboration reaction as well, and at the right top corner the link is also flashing. You can pause the video first. If you don't know how the hydroboration reaction takes place, then you can pause this particular video and click on the right top link and first learn this thing as well. Okay, so what will happen? One hydrogen will add to this particular carbon and another moiety will add to this particular carbon. And please remember, it will not make any difference if you add hydrogen here and Br here. Please remember this point. So I am writing that, please remember, this is syn addition, and in this syn addition, your top attack will take place. Okay, please remember. So when top attack is taking place, so I am writing this particular intermediate again. This is a 5-membered ring, and I am disturbing the right hand side bond in order to form the intermediate. I am not disturbing the left hand side. However, if you want, then you can do the reaction on the left hand side double bond as well. This will not make any difference in the product. Okay, so it is a syn addition. So what will happen? Hydrogen will add here, and the part, this is where boron, okay, and then this particular banana thing. Okay, so here you can see this is below the plane, and this B and this alkyl part on cycloalkyl part on the above phase, and this is also the above phase. That's why it is the syn addition, because both the groups are adding on the same side. Okay, and this is the less hindered side. I hope this is quite clear. Clear. So this is basically the syn stereochemistry. This is the first step. And then in the second step, what you will do, say this is my second step, and here what you have taken sodium hydroxide. And of course your hydrogen peroxide is also there. Okay, however, the important function is of only this NaOH. So what it will do actually in that case, in the this is hydroboration reaction, and now you will do the oxidation, and in the oxidation you will get your alcohol. So how you will get your alcohol? Please remember this particular step as well. Say this is your 5-membered ring, and this is just like that. This is my ester moiety, which is below the plane. This is Et, okay, and that boron part will convert into the alcohol part. So this is, you are getting your alcohol. I hope this is quite clear to you. If I go back in the previous slide, so this was my first step. Reaction was this one, and then H2O2, and this is P. It clearly indicates that this particular compound is my compound P. So you have done first step reaction. Now if I go back again, you can see here in the second step, first your methyl chloride is reacting, and then triethylamine. In the second step, you are doing the alkaline hydrolysis type of thing. In the third step, you are doing the reduction. So how we will do this particular reaction? Now I got my P. So what I will do? Now suppose I am having this my MESL. This is, say, double bond O. This is again double bond O. And this is my methyl, and this is the Cl. This is your methyl chloride. So what will happen, you know, this oxygen is having 2 lone pair over there. It can attack on this sulfur, right? And this chlorine will liberate from here as a leaving group, and then you will get your another intermediate, and you can very beautifully draw the structure of that intermediate by putting the double bond on the left hand side and putting my ester moiety in the on the bottom phase, right? And then you see this was my oxygen and this was my hydrogen, and now this oxygen is making the bond with that sulfur, okay? And you know, with the sulfur you are having this oxygen, double bond oxygen, and then you are having the methyl, okay? Since one of the lone pair of this oxygen has been used in the formation of the bond with the sulfur, so this will get the positive charge, okay? Now it is quite important. And in the next step, what you will do here, according to the reagents given in the reactions, okay? So triethylamine is given here. What is given? Triethylamine, Et3 and your N. So basically this is basic, and you all know this hydrogen which is present on the alcohol, it is acidic in nature. So what will happen? That particular nitrogen will attack on this particular hydrogen, and that bond will break and it will push the electron pair onto the oxygen atom, right? And you are having this byproduct. I am writing this byproduct like that, minus Et3NH, right? You can get this thing. Of course, your nitrogen will now positively charge and this hydrogen would be negatively charged, because nitrogen is having only the valency of the 3, and in that case it is having the 4. That means it is electron deficient. That's why I am writing this in that particular manner. And in the next step, I'll do my intermediate again. This is my 5-membered ring. This is left hand side double bond, and you know, this is my ester moiety, which is the below the plane, and this is my ET, right? And then I'm having my oxygen, okay? And that oxygen is connected with the sulfur, with the 2 oxygens attached to it, along with the CH3. So this, why actually this I have done here, because this is now a better leaving group. This alcohol is not a very good leaving group, but we have to eliminate this thing from here, and this will be done by the methyl chloride. So this is a better leaving group, please remember, okay? And in the next step, what will happen, if I go back, right? Again, I am going back to make the things little bit more clearer. See, this you have reacted, this you have reacted. Now you are having the sodium hydroxide. That means hydroxide ion you are having, okay? So what will happen? Then you will write your hydroxide ion, OH negative, right? Basically, this negative is present on the oxygen atom. This is the residual charge, okay? And you know, this is the base, and this is on the bottom side. Please remember, this is on the, this is on the top side. So this top side is crowded. So what will happen? This OH will attack onto this particular carbon atom from the bottom phase. Please remember, from the bottom phase. So it will react like that. It will attack from the bottom phase. It will attack here, okay? And then this bond will break. And when this bond will break, then this particular part, right, this will be eliminated from here. I will not write that particular point because particular intermediate, particular byproduct, because I am not having that much of space, but I am writing my this thing here, right? This was my 5-membered ring. This is my ester moiety, which was below the plane, okay? This is my CO2ET, okay? There is no problem in that, okay? And you see, when it is attacking from the bottom side, again it is producing, see this OH attacked here, this is producing OH kind of thing. Now you may wonder what you have done. You are already having this thing here and again you have produced this thing. What is the reason to produce this particular thing, right? So this is we have done to eliminate the water molecules, to eliminate the hydrogen from here. Okay, now if you carefully see, now this OH is below the plane. So all this thing which I have done from here to here, from P to get this particular P, to fix the stereochemistry of this particular OH, right? This has gone now and this is now below the plane. This thing I have done like that only. Please remember, this is very, very important. Okay, and then you see, since my solution is having the hydroxide already, OH negative, okay, and to make the things little bit quite clear, what I'll do, I'll write that single bond and hydrogen like that, and this negative charge will attack onto this hydrogen and it will shift this electron pair onto the oxygen. Your water molecule will eliminate, okay, and then you will have this species here, my 5-membered ring along with this bond, this particular group which is below the plane, this ester moiety, okay, and then this is what below the plane, my oxygen group, O negative, I can write like that, okay. And now what I will do, I can see, because I need to rewrite this particular structure, right, to give you the clear idea about the reaction mechanism. So what I will do here, I'll write like that. This was my carbon, this was my double bond oxygen, okay, and this was my oxygen, right? This is the ester moiety. So what will happen? This negatively charged species will attack onto this particular carbon, okay, and this will get shifted over there, okay, and when it will shift over there, so you will have another intermediate which will look like this double bond, okay, and then my below the plane moiety, this is my carbon, now this is single bond oxygen, this is my OET, okay, and that oxygen which is below the plane, right, now it has made the bond with this carbon, okay. So new 5-membered ring I have produced, 1, 2, 3, 4, 5, or I can number them 1, 2, 3, 4, 5. I have produced my new 5-membered ring. Okay, now what will happen, you can see here in the next step, this will come back, okay, rearrangement is taking place and this will be knocked out from here, okay, and when this will be knocked out from here, what you will get, you will get this particular intermediate. Again you see, this is my 5-membered ring where double bond is present on the left hand side. This is my bottom phase, this is the carbon now having this double bond already there, and then I am having this bond here, and this is my oxygen which is connected here. I missed my oxygen from here, actually I must write this oxygen here, okay, and you know this group will be eliminated, minus OET negative, okay. So this up to this point we have done now, and now if I go back, right, again it is very important to see the question again and again. This I have done, this I have done, now I left with the hydrogenation reaction only with the help of the Wilkinson catalyst, and I already explained the role of the Wilkinson catalyst. So here I'll do the hydrogenation. That is H2. I'm sorry. That is H2 in presence of Wilkinson catalyst. So again the hydrogenation will take place, and when the hydrogenation will take place, what will happen? This double bond will also convert into the single bond. One hydrogen will add to this carbon, another hydrogen will add to that carbon. Okay, and then you will have this particular product, this, and this is my ester functionality, and this was my oxygen, this is my carbon connected with this one, and double bond oxygen, right? So this say my final product, and I can name this final product as Q. So this was my P and this was my Q, right? You can write down this particular these two particular product in the copy, right, or your answer sheet to match the answer correctly. So here you can see this, my in the P, my ester is on the bottom side, my OH is the top side. So now I go back, I'm going back, right, my OH is up and my ester is down, and this double bond is intact here. That means this is correct. Okay, and now if I coming back onto B, B is not possible, because you see the vicinity according to the reaction mechanism must be in the vicinal carbon. The OH must be present on the vicinity of that this ester moiety, but here it is not present in the vicinity. That means B cannot be your answer. If I go back onto the C, C is having the same stereochemistry of the product P as of B. Both are same. That means A and C could be correct. Okay, now coming to the third one, again third one is not possible here, you can see, right? So this again, see A, you can clearly discard your B, and you can clearly discard your option D. And in the option D you can see here different kind of the product where your higher membered ring is forming, and you have seen already in the reaction higher membered ring is not forming, so you can discard option D and option B. So the competition is in between the option A and option B. Now look at the stereochemistry of this particular compound. This is on the bottom side, this is on the bottom side, but here you see this is on the bottom side, this is on the top side, and you have already seen your syn hydrogenation was taking place. And this is, see, this is not feasible actually. If you are forming the 5-membered ring and one bond is below the plane and one bond is above the plane, this is quite awkward in the stereochemistry, or for the stereochemistry of the compound, for the stability of the compound as well. So this cannot be the answer. So your right answer actually is looking option A. Now let us take a look again. You see, right, this is P and this is your Q. So this is how you can approach such type of the questions. These are very, very important thing. I hope you understood the concept quite well. If you like the lecture, please give a thumbs up to the video, and if you are watching video for the first time, please subscribe the tetrahedron chemistry classes and do share with your friends as well. Okay, I'll meet you in the next class with some other very interesting topic, right? So that's it for today. Thank you very much.